Hey there. Today we're gonna do a differential equation to solve for air drag. Um, well, we're solving for terminal velocity and air drag. So we'll start off with Newton's second law equation, and then we'll create an equation for terminal velocity. So to start off, just to go over what terminal velocity is, we have an object under the force of gravity. So there's mg. We also have a resisting force known as drag force, or air drag in this case. So what that basically does is it's a resisting force. We have our air pushing that way, and this resists the ball from the bottom. So this starts off really small, and then as the ball picks up speed, this is going to also get larger. So at some point, our mg and air drag is just equal to BV, negative BV, the force. So we're gonna be at a point where the air drag is equal to the force of gravity. At this point, we're at equilibrium, and our acceleration is zero, which means that our force is also equal to zero at terminal velocity. So this is an important thing to note. With this given, we can actually get started with our differential equation. So to start off, let's write our equation. So we're just worried about air drag right now since we're just solving for terminal velocity. So we don't need to worry about um, our force of gravity here. So which is we have our force drag, which is equal to negative BV. And this negative BV is technically equal to our MA because that's the force. So MA is equal to negative BV. And notice we have our A term here, and we have a V um, value as well. So we want there to be the same letter throughout so that it's easier to solve the differential equation and integrate. So we represent V, or we represent A in terms of V. So we all should know by now that acceleration is just the derivative of velocity with respect to time. So we can replace A with dv dt. So m dv dt is equal to negative b v. So this right here is our differential equation. Now, in order to solve it, we need to start off by separating the dv's and the dt's. So what we're trying to do is, let's see here. Let's bring the m's over to this side, and then the sorry, let's move the dt's over to the other side. So just m dv. Hang on, I got mixed up for a second. So yeah, as I was saying, we're gonna move the m over to the other side so that we can bring the v over, and that'll be nice. So when multiplying by m on both sides, we have just our dt is equal to negative, or sorry, I meant dividing bv over m. So now we can actually multiply both sides by 1 over v to cancel the v's out. So multiply by 1 over v and move the dt over. So multiply by dt on both sides. Doing that gives us negative b over m dt, which is equal to, what is it, 1 over v dv. these d's cancel out, these dt's, and then the v's cancel out here. So now that we have all our v's on one side and the t's on the other side, we can start integrating. So we can take the definite integral of 1 over v dv from the bounds of v naught to vf and set that equal to the definite integral of negative b over m dt from bounds of time 0 to time t, which is our final time. So now just evaluate the definite integral. Notice this resembles 1 over x. So the integral of 1 over x should just be ln of x. Uh, you should know that from calc. So let's just use that rule real quick. And then this just becomes ln vf, because that's our final, minus ln v naught, which is equal to negative b over m are both constants. So just add the t term to it, and then you just get negative b over m t from the bounds of 0 to t. It should be, hold up, yeah. So just simplifying this further just gives us, yeah, so that's just negative b over m t, because that's our final, which is equal to this. Right. Do notice that when we have two logarithms, natural logarithms subtracted like this, that means that they're actually being divided. So that's a log property. So if we have ln of a minus ln of b, this is just ln of a over b. This is a property for logarithms you should know. So apply that, and then we should get ln vf all over v naught, which is equal to negative b over mt. Oh, great. This is pretty much all the hard work done here. And now that we want to, we're trying to find VF, right? Since VF is technically our terminal velocity, that's the final velocity, so that's terminal. So we're trying to isolate that, but then it's inside a natural log, so we have to take both sides to base e to cancel the natural logs out. So let's do that. So we have base e of, for the natural log of vf over v naught, which is equal to base e of negative b over mt. The e and the natural logs cancel out here, so we're just left with, I'm going to switch over to here, which is just vf over v naught is equal to e negative b over mt. And finally, since we're trying to solve for vf, we just multiply both sides by v naught, so we should get e, so v naught e to the negative b over mt times t is equal to vf. And this right here is our expression. I'm going to erase some of this and then write it up here again so that you can see it better. So terminal velocity is just v naught e to the negative b over mt which is equal to Vt, which is equal to Vf. There we go. All right, thank you guys for watching. Please leave a comment and subscribe, and see you later.